So now, again, going back to the MNIST problem, now I want to basically train a TensorFlow job. So this is a very simple TensorFlow network. It's a two-layer, fully connected TensorFlow job, which what it does, it basically gets the data from the data set, which we just like imported. Again, this is defined as the, is what it does, basically gets a file. If I'm a local, again, is accessing the data, which is on my local computer. I download it to my MNIST folder within my local computer. And basically it loads them. I already loaded them into 4 different variables: xtrain, ytrain, xtrain, xtrain, xtest, and ytrain, ytest. And now I want to pass it to the network and build my model. So what it does, basically goes through a couple of epochs, and I pass the epochs, like define the epochs through some variables. Very like basic stuff, nothing very fancy. So now I basically hit run. So when I run this, it basically gets executed on a local computer. So like it loads the data, goes through every epoch, and in every epoch it tests the accuracy on the training set and the validation set, and comes up with 2 numbers. This is mostly the way that we do things, but in order to leverage those run metrics, what I want to do, I want to basically track these values which are happening here within my experiment through a run. It's too big, it's not scrolling well. So now it's getting through every of the epochs. And yeah, 13, 5 more. So we already had a run before, right? So what I have to do, I have to basically complete the previous one because I want to start a new experiment, right? So I complete it. Right? So now I want to create a new experiment, which is called like train TF locally. And what I want to do, I basically want to keep track of all of the parameters that are happening here. Like those parameters that are passing as hyperparameter, I want to keep track of them. Some information about the data set, I'm going to skip through this. But then these are like all of the variables which I basically downloaded, and I basically loaded into a NumPy array. These are all NumPy arrays of normalized data. Yeah, sure. And now I want to run my TensorFlow job again. But this time there's a difference, and that's the run.log. So within this time, I want to basically keep track of every of these metrics within the epochs. And then finally, I want to upload the model into a folder called outputs ML. So basically that the final model which is saved will be uploaded to the run, which is associated to this run object. So now going back to this, so you see that again is happening, is saving the data there and is streamed back through this widget. And you can of course see it here, what's going on there.
But this is all using MLflow in the background, right?
No, this is on, but you can talk to MLflow. You can save it to the MLflow basically. Yeah, they worked very close. Basically, like we worked very closely with Databricks to basically have these 2 technologies work together as part of the Databricks. Yeah, and also but you cannot save these in the SageMaker because that doesn't have the experiment part. You can only save it within Azure ML workspace, basically. Yeah. But you can register the model within SageMaker. Yeah, that's the part which is supported. Yeah. So now it's completed. Again, if I get the runs, I will be able to see everything which is happening here. But that's a little bit better way because I'm actually now collecting things. But in order to make it reproducible, what I want to do, I want to make the compute node also reproducible. So For those who have Docker background, if you don't have it, just ignore this part because that doesn't have any impact on the continuation of this workshop. What I want to do, I want to basically create a remote computer within the cloud, let the Azure ML discover what type of Docker image I want to deploy there. What Docker image helps me to do is basically to eliminate a lot of installations and dependencies on that remote node, and then submits my TensorFlow job to the one that I executed here to that remote node. So in order to do that, first I create a compute target. So by running this code snippet, what it does, it basically creates a computer. It's a GPU. It's called NV6. It's a half of basically GPU. Super like virtualized GPU, and is only one node. But in reality, in real life, you may definitely pick a much bigger node, like from 0 to much bigger. I didn't pick 0 because it will every time it will have some warm-up time. I don't want to waste my time there. But basically, because of the limitation of subscriptions, free subscription, I want to only pick one. Please do not change this for yourself, and make sure you turn it off after you created that. Or you set 0 here, where it goes back to 0 every time you don't use it. So again, you don't get charged once it is load back. Because I already created one, it returns the compute target pointing out to that node, which I created outside. Again, that's a computer which is created right now on demand. If I go to the workspace under the compute, I basically can see that here. That's a GPU cluster that I created. So again, every time I refer to this object, I'm referring to that remote computer, which I basically create in the cloud. So I'm going to skip this part. But going back to that concept of Dockerization, there are some level of abstractions happen in the Azure ML to basically eliminate so many of the complexity around the Dockerization. There's a class called TensorFlow. So if I create a run or a type of submit my particular TensorFlow job to a TensorFlow class, using the TensorFlow class, Azure ML understands that it has to deploy a particular version of Docker to that target compute. Therefore, I don't need to explicitly provide that. So I can just completely be, yes, please.
So I have a question.
Yeah.
So this whole part just covers, say I already have the clean data, I want to train the model, and I want to evaluate the model. But if I want to Dockerize or I want to automate, say, the ETL part, just in the map in general direction, where would I put that?
So when you would Dockerize it, right?
Yeah, like I have an ETL part. Like I load, say, an SQL database, I load a Mongo database, and I load some whatever.
So this is not basically related to ETL. Is basically related to training, actual training pipeline. So the training ETL happened before. We don't want to discuss that. So at this time, I want to create a computer somewhere which loads the data in and trains my TensorFlow, my model using TensorFlow job. Yeah. That's basically the focus of current discussion, and it's not the ETL part.
Yeah, I get it. That's why I asked, like, where would you put the ETL part?
So the ETL part is outside of this. Yeah, ETL is not part of the MLops lifecycle. It's outside. It's called data ops, which is another giant discussion. Yeah. Okay. So now, what I want to do, I want to basically leverage that. So again, what I did, I created a remote computer, and I want to basically be able to submit my TensorFlow job to that. So this is the TensorFlow.py file, which does the MNIST, basically exactly the same algorithm that I basically ran there. At the beginning, I'm passing some parameters as the arguments. Basically what it does is look at some channels that I basically can point in and injecting some information to my Python job. And I can basically pass some arguments to those. So the important values are the data folder, the batch size, first layer neuron, second layer neuron, and layer. Basically by changing these, it will basically act differently. And it will generate a different network for myself. So what I want to do, I want to submit this TensorFlow job to that remote computer and get executed. So in order to do that, I first construct a dictionary which explains all of those parameters that I want to pass to that object. The first is a data folder, and the rest are provided. The part which is interesting here is that I want to basically point out that default data store that I have and mount it to the compute at the execution time. So they will be connected together, and it basically will treat it as a local storage. And so this dictionary will be used as a parameter here in the TensorFlow object. And so what it does, what's important here is this TensorFlow.py, which is the entry point. The folder which keeps all of my project files, like if you have like 10 different files, you will have to keep it within the script folder, which is pointing out to a location within my local directory. The script parameters, and also the compute targets. Again, I can define different types. I can define local. I can define something in the cloud. Then I can also provide some packages that have to be installed, right? So the TensorFlow will instruct the base Docker and some oops. It defines basically the base Docker and some of the packages like CUDA and other stuff that needs to be installed on the remote computer. But also I can provide more like Conda package and etc. if I want to instruct it further. It got refreshed, so let me go back to the Jupyter. Any questions so far? All good? Or all not good?
So
yeah.
I thought you're gonna go through the notebook and then you give us 20 minutes to do this.
Just a few more minutes. I will give it back. Your thought is correct.
Just can't wait.
Yeah. Yes, definitely. Not a lot is left here. Okay. So, so now let me comment this out to save some time. What I basically do here, I'm now submitting this job. Oops, I need to call this one. So what I do, I submit this TensorFlow.py and everything which is within that folder to that remote computer, and that get executed in the wild. So there's some like abstraction for PyTorch, TensorFlow, chainer, and scikit-learn, where you can of course like submit a custom algorithm through a class called Python script. So it can be any custom algorithm or anything which is not it doesn't require any prepackaged or something they define in the past. So that gets executed within the node in the wild. And again, the logs and everything will be saved. So every time you submit this using this TensorFlow class and using experiment submit, it will start a new run, and it will complete it after the job is completed. And everything happens within that remote computer will be saved under that run object. So again, like these are all of the values are logged within that remote computer. So again, the remote computer got that file, is now executing this, and these are the prompts or the prints which is happening at the remote computer. Yes, please.
Wait until this run is complete, and then you can run another run.
So you can. So it is not non-blocking by default. So once I submit this, I can still continue developing here because that is running there, and get everything back here. But if you submit a new one, it will get queued after the other one. Yeah. So that's basically one way to do that. And now after it is basically completed, if I run register model and provide a name, what it does, it will save it within the model registry. There are a couple of important things here. And one is within this file, I'm saving some information within the output folder. everything which is saved within the output folder within the TensorFlow job will be saved as part of the run. So now if I go back again to the experiment within the cloud, if I go to the experiment, if you remember, I named this experiment as, yeah, what was that? Can't find it. It was TF locally, or no? Yeah, it was called TF locally. I called it TF locally, but I didn't train it locally. I trained it in the cloud. So this is the run that I just submitted. So when I go inside, there are like 4 main categories here, which will basically keep track of everything which happened there. If you see, these are like the target compute, which has happened, the run ID, and etc. But there's a folder called outputs. In the outputs, if I save anything within the output folder in the local execution node, if a local computer orders something in the wild, like in the cloud, it will again load everything and attach it under the output folder. And the logs are the files which keeps track of everything which is happening on the local on the execution node, and the snapshot saves everything within the script folder. So my code and everything was within the script folder. All of them again will be saved here. So now I know that exactly what happened in the run 16. So exactly what happened, all of the parameters that I submitted, the environment, the actual node that was completed, the data set that was used, and basically like the entire lineage can be basically extracted there. So now I skip a little bit, and
you have all the version numbers too, right? Like if TensorFlow changes, like you have all the version numbers.
yeah, so basically I can provide the different types of like TensorFlow versions here. And based on this, it will be deployed a new Docker. But again, you can provide your custom Docker too. Like this is basically to simplify the life. But you can provide, you can package a new Docker image and say, I want you to use this Docker image that I basically created. This is basically to simplify and covers most of the general cases basically. Yeah, so again, once you run this, what it does, it will basically gets the data, gets the model, and saves it under the model registry. And this is the one. Because I saved it twice, it will get 2 versions. And every time I can get the version I want and download and play with it. There's another way to submit the job, which you're gonna skip, and just go very quickly, and that's the parameter tuning. So what you can do here, instead of submitting one job at a time with a set of parameter, you can basically define a range of parameters. Like going back to this, these were basically those parameters which you could pass to the job. But instead of one, I want to provide multiple. It can be discrete or it can be continuous form, and then it will be submitted to the local to the remote computer. And based on the way that I want to sample my hyperparameter space, it's like a Bayesian optimization, greedy or random sampling, it will come up with that method and start to come up with the best next guess to choose. If I have like 200 nodes of a cluster, if I had like 1,000 permutations of hyperparameters, it will basically run all of them at the same time simultaneously. And that's mostly what happens in real world settings. You have so a gigantic cluster and submit all of them together. So I now, let's start downloading this, cloning this to your computer, and or the Azure notebooks, and then spend some time on it to get to the next stage. Thanks. Yes, please.
If we're not using the West 2, I don't know, data center, if we're using like Canada Central, for instance, what's another VM that we should spin up with the GPU?
Yeah, so please stick to the West US because the VM types will different, especially for the NC, for the N series, which are the GPUs.
Okay.
So stick to US West 2 because that will simplify the life. Yeah. Yes, please.
I have the same issue.
Yeah,
I was
Yes.
checking the price.
I'm sorry. Please get to this slide. Get to this repo, clone it in your local computer, and start playing around with it. Yes, please.